Okay, I will check your attendance. 이혁재 씨, 고하늘 씨, 네, 고하늘 씨, 심준호 씨, 네, 심준호 씨, 이승빈 씨, 네, 이승빈 씨, 이정태 씨, 네, 자, 이충하 씨, 네, 이충하 씨, 정상아 씨, 네, 정상아 씨, 그리고 홍주표 씨, 네, 홍주표 씨, 김민선 씨, 네, 민선 씨, 김유신 씨, 배민열 씨, 아직 안 오셨고, 배서령 씨, 아직 안 오셨고, 서하연 씨, 조대현 씨, 네, 조대현 씨, 최승주 씨, 아직 안 오셨고, 김성수 씨, 김성수 씨 아직 안 오셨고, 미스터 마니큐, 오케이, 마니큐. 다시 한번 불러보겠습니다. 이재혁 씨 계신가요? 네, 이재혁 씨. 그리고 이정태 씨, 네, 이정태 씨. 또 배민열 씨, 네, 배민열 씨. 배서령 씨, 배서령 씨 아직 안 오셨어요. 최승주 씨, 최승주 씨 아직 안 오셨어요. 김성수 씨. Okay, so welcome to lecture 24. This is the second last lecture of our semester. So yes, we have done many lectures. So in offline form and online form, and we are finally here. Okay, so as I told you before, we will just follow the regular schedule for our final examination. So as you can see here, the June 13th here, Monday, we will have the offline final examination as usual. So please come to the designated room. So I have no idea about where it is, but you know. Yes, so that is already known to you. So please come to here 2 weeks later. And unfortunately, due to local government election, so in this Wednesday, we have no lecture. Also, due to Memorial Day, so 6, we have no lecture. So we have just 2 remaining lectures today and June 8th. So we will have just 2 remaining lectures. Yes, and as I announced already, so I will try to cover the digital related topics in these 2 last lectures. Okay, so and also you know that our TA, Mr. Kwang Lee, is really smart and fast. So I think that you have almost all of your homework problems scored almost immediately. So just 1 or 2 weeks you have the score. But in my case, actually, I'm a lazy guy. So although several weeks has passed, but I have not finished your midterm examination. But as I told you before, so this day, so this June 8th, you will have the score for your midterm examination, and also you will have some chance to check the correctness of my score. So please have the time to review your score and the answer of your digital examination. Okay. Do you have any question about just those things, like not directly related to the technical content, but some exam or homework? Okay. So if you don't have any question, then let's go to the second part. Yes. So if you have any question about technical contents in our lecture, so please give me questions, then I will be happy to answer your questions. Okay, so we have already mostly covered the part related with the analog. So actually, in usual configuration of microelectronics course, actually the amplifier part is at the center of that one. So, but instead of solely devoted to the amplifier part, so I just made a small slots, a few or actually two time slots for our digital part. So if you have any question about amplifier, then please let me know. So that is, I think that the most important one for that was the most important one for our entire semester. Understanding the behavior of single-ended amplifier was the most important one. So, okay, so if you don't have the immediate question to me, then please feel free to send me an email about your question, then I will be happy to answer your questions. Then I assume that you have no further question right now, so at least in this place, then I will just move to our lecture 24th. Okay, so from today's lecture and the final lecture will be devoted to the digital circuit, but you know that digital circuit is really best area. So it's not possible for me to make any kind of reasonable overview on this digital circuit. So instead of that, I will just focus on a specific circuit you have already seen it before. So that will be logical inverter. So simply speaking, it means that your logical 0, so logical false is converted into logical 1 or logical truth, you know. So the same happens to 1, 2, 0 transition, so you know it. And even further, we have already seen this simple realization of inverter by using this same circuit with the CMOS amplifier. So if we define this voltage as input voltage and also define this voltage as an output voltage, then approximately the relation between our input and output voltage follows that of desirable inverter logic. Okay, so are you with me? So that's the reason why we can say so was, yes, say this is out and this is in. Then when we have, for example, exactly 0 input voltage, then our output voltage is also exactly VDD. So we have 0 comma VDD, so pair for input and output voltages, and that can be interpreted as, okay, if you give me logical false, then I will generate logical true. That is simple rule. And when you go to this part, what was it? So when we have actually VDD as an input voltage, then yes, think about this guy. Yes, now we have VDD. Oh, now our gate overdrive voltage is given by VDD minus VTH. So our transistor M MOSFET is highly turned on. So we have a lot of electrons collected in this part. So we expect that, oh, there will be quite a strong current conduction through our resistor. If we have high current, then what will happen? The voltage drop across this resistor, or let's say that this is RD, then we will find that the voltage drop will be simply given by ID, drain current of our transistor, and multiplied by RD, so the resistor connected to our drain terminal. So since our original value at this point was set to be VDD, so we just added our voltage source to this part, so we can easily understand the output voltage is given by VDD minus ID RD. You know, this one is given number and this one is also given number. Only variable thing is ID, and ID is a function of gate voltage. So if we have high gate voltage, for example VDD, then we expect that, oh, this ID will be quite large, so voltage drop is also large. So output voltage VDD minus ID RD will be small. Yes. However, what we can say is it is not exactly 0. So we can expect that the ideal case would be like this. Yes, if we can have VDD, 0, then that will be regarded as the ideal case for our inverter realization. Okay, logical 1 is exactly converted into logical 0. So now we have certain kind of symmetry. Okay, our 0 is converted into strong 1. So what is a strong 1? For example, think about this guy. Yes, now we have this cross point. Let's assume that for our certain inverter implementation, let's say that this is our output. Then will you say this is the failure of your inverter design? So I mean that. Let's think about a certain artificial system, like in, out, and our VDD is given by this one. Yes, this is logical 0, and this is logical 1, and this is logical 0 and logical 1. And unfortunately, due to our inability to make a good design, so unfortunately, let's just say that our system just follows this kind of voltage transfer curve. So whatever inside it, that doesn't matter. So let's assume that when you insert 1, your output value is not exactly VDD, and when you insert VDD, then your output voltage is not exactly 0. So what will happen to your constellation? You will say that, okay, this one and this one, of course it is not exactly VDD or not 0. But if I ask you, please say yes or no, is it close to VDD or close to 0? Then anyhow you have to say this is close to logical 1 and this one is close to logical 0. Yes, if we have to anyhow make just black and white, or 0 and 1, or red and black, so if we make just judgment, then we will say that this is 1 and 0. Then compared with the ideal case, yes and yes, do you like it or don't like it? Of course you don't like this implementation, and you will say that this one is just too weak and weak. means that you have a certain deviation from the ideal values. So if you have just 0, oh, you will be quite happy. If you have just 0.1 volt, that is also treated as logical 0, but the strength of this zeroness or null close to the null is a little bit weak. So that's the reason why we just say it as or call it as weak. So let's come back to our implementation. Then if we have just voltage transfer curve for our Nmos and serially connected resistor, so usually it is called as Nmos inverter. So inverter which is implemented with on Nmos, that is the reason why we call it as Nmos inverter. So in this case, please name the strength of their output. So we can say that, oh, this output is really strong. So always we have the value of VDD. But unfortunately, this guy in this 1 to 0 transition, our output is rather weak. So yes, that is the problem. So we wanted to have a better implementation. Okay. So of course, I wanted to say this one. For example, think about this guy. If you have two serially connected Nmos inverter, then please think about this case. You add just you here insert logical 1 and you have two inverters, so one NOT and another NOT gate. So what is your expectation for this overall output? So what you can expect is just logical 1. Why? It is simple, because you have the conversion from 1 to 0 and 0 to 1. Eventually you will have just the buffer, so nothing is changed and everything is just copied into your case. But think about this buffer implementation. If you have two serially connected Nmos inverter, then what will happen? Here, 1 from 1 to 0, you will have strong or weak 0. You will have rather weak 0. So are you with me? Because it will generate a slight output voltage higher than 0. But fortunately, if we go to the second stage, so even though we have weak 0 as an input, but fortunately our implementation just follows this kind of a loop. So if you have if you give a weak value for your input, still you have VDD. So that's the reason why still you have a strong output. Okay, so it means that even with this not perfect inverter, so called an Nmos inverter, if we introduce this kind of buffer, so which is just serially connected inverters, then you can always recover the signal. So yes, you have a strong something which is not very strong, but you can make it. But anyway, if we consider the opposite way, then maybe that is not the case. So if we have a 0, then end of this loop, you will have once again weak signal. So point is, the ideal case should be not like this. You have to have a certain transfer curve, ideal transfer curve like this. Let me just okay. So okay, this is the largest one I can have, then the ideal case would be like this. Can you see it clearly? So I'm not quite sure how can I introduce a thicker line for my drawing. So instead of that, I will just draw in this green line, thick green line. So if we can have such kind of a voltage transfer curve, so maybe you will be quite happy. It means that, let's think about the beauty of this voltage transfer curve. It has certain property, like if your input is weak, so if your input is not exactly 0 but have a certain deviation from 0, okay, this is not very strong signal, but anyhow you have a certain signal which should be regarded as logical 0, then what will be the answer? The answer is always quite strong logical 1. Oh, good. And think about the opposite case. If you have certain bias input voltage which is belonging to this area, then although your input signal is not so high, not quite close to VDD, but still you have quite a strong output. So simply speaking, ideal case would like this. We can think about the range of our input. It can be located between 0 and VGD, and we can label this is a strong signal and this is a strong signal, and they are weak signals. Oh, point is, if our implementation is really ideal, then what will happen to our signals? Our signal, all of them are just converted into strong 0, and strong 0. So are you with me? And also in the case of this logical 0 case, input logical 0, although we can have weak signal, but that is always converted into quite strong our output voltage. So that is the beauty of or strength of our idealized implementation. So first of all, before continuing our discussion, you have to understand this point. What is our goal? What is our goal for improvement? If we can achieve this kind of voltage transfer curve, then we will be very happy. If we cannot achieve this one, maybe our logic is not that strong. So in the case of our Nmos inverter, so we have weakness for this part. So do you have any question on my discussion up to now? So the discussion up to now clearly reveals that we wanted to improve our implementation for inverter. Okay, if you understand this point, then let's think about how can we improve this implementation. Any question? No? No question? Okay, then let's go to this part. So actually, yes, we love it. Yes, we are already quite happy with this part, so we don't care about that much. But point is, the non-ideality comes from this point. Yes, so when we insert or when we give the logical 1 as an input, our output is not exactly 0. That's the problem. So let's just think about the actual implementation of this guy. So think about the case where we have input sorry, where we have input VDD. Yes, I think that okay. So now we have VDD as a gate voltage, and now we have transistor. Yes, and yes, and we wanted to have yes here V out, however, which should be so in our ideal case it should be 0, but you know that cannot be a case. So in reality it is not 0. That's the problem. So think about this guy. How can we divide these voltages across these two serially connected electronic components like MOSFET and transistor? So in this case we have VDD, and that should be distributed either to this resistor and yes, this and MOSFET. So think about that VDD case. Gate voltage is VDD. Then what will happen? If we have the maximum voltage which can be applied to our N MOSFET, what we can expect is, okay, this guy becomes really highly conductive. And yes, this resistor is always, yes, please note that this guy is always resistive, and the amount of resistiveness is called as a resistor. So please note that this guy is just fixed, and its resistiveness or resistance is given, and only the conductiveness of this MOSFET is directly controlled by our MOSFET. So the case is, now yes, this guy is given, and since we have increased our voltage up to VDD, now our N MOSFET is so highly conductive. So from the viewpoint of this VDD, now it just consider, I have a VDD. Who will take this voltage? Then who will take that voltage? Most resistive one will take the most of our voltage. Yes, you know it. So if you have serially connected resistors, think about this one, R1, R2, and VDD. Who takes the most of your voltages? VDD. If you have high resistance R1, then that will take it. So the one taken by R1 is given by just R1, R2, and R1, and the one taken by our R2 is given by VDD R2 divided by R1 R2. So simply speaking, it is so simple. If you have a highly resistive guy, then that takes all. Then think about this guy. This is true once again. Your idealized case is V out equal to 0. But unfortunately, what happens? Unfortunately, the reality just comes to here. Why do we have this marginal small voltages as an output? It is simply because, yes, this guy and that guy just competing to take the voltage VDD. The voltage division occurs, but however, this small voltage, output voltage, just to indicate that, yes, this guy, the resistor, drain side resistor, has higher portion in total resistance, but that is not, please note that, that is not overwhelming large. So they are comparable. For example, let's think about this guy. 10, 1. Oh, that is big difference. So if we have just 1.1 volt, and the output voltage will be just 0.1 volt. But what you want to get is not 0.1. What you get is just 10 to the minus 6 volt, or even smaller amount of voltage. So that's the reason why we have a little marginal values. So instead of this 10 to the 1 ratio, let's think about if your resistance have this ratio, 1 million to 1, then what will happen? Then if we have such a kind of ratio, then it is true that your output voltage will just follow 10 to the minus 6 times VDD. Oh, so what you can expect is, if we really wanted to have high distinction between this resistive here and there, one possible way is just to make it more highly conductive. Simply speaking, if we have wider MOSFET, then what will happen? When we apply VDD into our transistor, then if we have wider channel, then our transistor becomes more highly conductive. So although we have a resistor, fixed resistor, but the relative ratio or output voltage here will go down. So are you with me? So simply speaking, I will just give it to you as a homework example, homework problem. So if we have wider and wider channel, then this will reduce. The output voltage will reduce. Good. So simply speaking, if we have, for example, quite a large one, quite a large MOSFET, then what will happen? Then when we apply this VDD, then our MOSFET becomes highly conductive. So we will have a very closed value instead of this marginal output, unwanted output voltage, non-zero output voltage. But do you like it? We immediately find that, okay, by increasing your W value, then you can reduce this value. But then what will happen to your other side? Here. There you have also different behavior, unwanted behavior. So please check it. The point is, now I think that you have to understand this one. The output voltage shown here is obtained by just competition between our MOSFET and resistor. That is the point. Okay, so let me just delete some of unnecessary drawings here. Okay, so simply speaking, let's make a new view on this system. So simply, here we have two components, one component and another component, and that is grounded. Here we have a VDD and ground, and in between we have output voltage. So the output of this system is simply given by, if this one gives highly resistive and this one gives highly conductive nature, then what will happen? Yes, this highly conductive one provides us really good electrical connection between this output node and ground node. Yes, they are well connected. So our output value will be quite close to 0 volt. On the other hand, let's think about the opposite case. If we have highly resistive low one and highly conductive upper one, then what will happen? In this case, we will have just VDD as an output voltage. That's true. So now think about our N MOSFET. What happens to our N MOSFET? In the case of N MOSFET, so if we apply logical 0, then it becomes really highly resistive. You know that transistor has so ID versus VG, which is in logarithm. Even in this logarithmic sense, they shows quite much differences in this and that point. So if we apply 0 gate voltage, then this guy means that this N MOSFET becomes really highly resistive. Then how about this upper part? Upper part is always just a resistor. Its resistance is just given. So why do we have certain inequality in its conductance behavior? This guy is fixed and this guy is dynamically changing due to gate voltage. So since N MOSFET becomes too highly resistive, that's the reason why, although this upper part is just kept as before, but N MOSFET changes its behavior. So that's the reason why sometimes the inequality becomes to here or becomes to there. Okay? So now you understand this case. So if we have VG equal to 0, the case is N MOSFET is really highly resistive, and this guy, unfortunately, it does not change its resistance. But it's okay, because yes, this N MOSFET really becomes so highly resistive. But unfortunately, if we go to this case, VG equal to VDD, let's think about this guy. Now N MOSFET becomes, or N MOSFET shows its full ability. It shows its maximum conductance, so in terms of number of electrons. But unfortunately, who decided this output? Yes, in this case, this resistor upper part should be, that is ideal to be really highly resistive. If we achieve this configuration, then this one is highly conductive and this one becomes really resistive. Then we will have just a logical one, because this test is most unwanted compared with this test. So that is quite simple. You all understand. So now we have to blame which one. Which element should be blamed about this poor performance of our Nmos inverter? Who is guilty? This guy, Nmos do its best. Sometimes when it is turned on, it gives us highly conductive channel, and when it becomes 0, its voltage is 0, then it gives us really highly resistive one. But there is one guy which does not, its conductance. Who is it? Yes, this resistor. It just stay there. Oh, I'll just provide just constant resistance. So please, Nmos, you guys just change the conductance. So let's make a comparison between me and your dynamic conductance. That is the situation. But think about the alternative way. Think about this alternative way. That is really fascinating. So let's think about one certain ideal case. Let's say that we have VG equal to 0 volt. Then now our MOSFET becomes resistive. Then let's assume certain case where this upper part element is no longer a resistor. Instead of that, now let's assume that this one becomes highly conductive. Who knows? Up to now we have not discussed about this circuit element, but anyway, let's just assume the existence of such a kind of circuit element. If we have this kind of thing, which really shows highly conductive behavior when the input voltage is 0, then please estimate what will happen to your output voltage. So when you make a comparison, these two conductive one. So yes, this is resistive and this is conductive. So we have quite a strong connection, relative connection to here. So our output will be just VDD. That is just as usual. Even Nmos inverter achieve this goal. But point is, now let's go to the opposite case, the problematic case, like gate voltage is VDD. Then what will happen to our MOSFET and this upper part element? Here, now it becomes highly conductive. Good. However, previously in our Nmos inverter implementation, the upper part element was a resistor and it does not change its resistance value, equivalent resistance value. But let's say that now it becomes highly resistive. Let's assume, if we assume the existence of such kind of circuit element, then please estimate the output voltage. Now the electrical connection between output voltage and VDD node is effectively disconnected, and instead we have a strong connection between our output node and ground. So we will have just voltage quite close to 0. So how close to 0? It really depends on the relative magnitude of the strength of electrical connection between this test and that test. So are you all with me? So now you think that if we can introduce such a kind of imaginary circuit element into our scene, then we will be quite happy. So if we have such kind of thing, then we can achieve once again this beautiful voltage transfer curve. When you have 0, you will have 1. When you have 1, yes, still you will have 0. That is the main discussion in our first part. Okay, so let's just have some time to think about all of this. Up to now, I have tried to persuade that we need another circuit element whose conductance should be changed according to the gate voltage. Yes, previously, resistor is just a resistor. Whenever you apply something, it doesn't change its conductance or resistance. But now I'm saying that we need certain circuit element which react according to the gate voltage. However, exactly in the opposite way to that of N MOSFET. When N MOSFET is highly conductive, this imaginary one should be highly resistive. Instead, if we have a high, when our N MOSFET becomes highly conductive, yes, so they should be also, it should be also show the opposite behavior. So can you imagine such kind of circuit element? That is the second part of our lecture. Okay? So, but please note that if you don't understand the necessity of this new element, then our next discussion will be meaningless. So please note that if we have this kind of thing, this means that here, this guy, which takes the upper part of our configuration, that really important for our discussion. Okay, so then any question from students? So let me just make a table. So now we can say N MOSFET and something, and for ideal implementation of our inverter, we have this behavior. When gate voltage is 0, when gate voltage is VDD. So let's fill out these 4 empty places. So I think that you can easily fill them out. So now it becomes resistive, conductive, and if we go to this second column, then what will happen? Yes, it becomes highly conductive when we apply 0 volt, and it becomes highly resistive when we apply high gate voltage. Then you may say, you may ask this question: how can you get such kind of the opposite behavior? You know that. Think about N MOSFET. How did it get this trend? Why do we have a higher conductance when we apply higher gate voltage? So it was simply because the structure itself. So think about this one. The structure, do you remember the structure of N MOSFET? So at the center of our implementation, now we have a capacitor, and gate is located here, and if we increase the gate voltage, then we will have more and more positive charges here, and more negative charges here. And which one is used for electrical conduction? Yes, this guy was used for our electrical conduction. That was the case. Then now we wanted to have the opposite direction. Then how can you get such kind of thing? If we decrease the gate voltage further and further, if we decrease the gate voltage further and further, then what will happen? In this case, still we will have, yes, certain voltage where we have just a neutral part, but if we go beyond that part, then what will happen? Now we will have negative charge and positive charge. So of course, think about our N MOSFET discussion. When you consider N MOSFET, of course, always we can have, negative charge. However, we can think about 2 possibilities to have a negative charge. What was it? One was just to fix the dopants. When ionized dopants are negatively charged, and they can provide us negative charge. That was the first reaction of our MOS system. When we apply high gate bias, we have a wider depletion region, and we have more negatively charged ions. However, once we go beyond that level, then what will happen? Then we will have mobile electrons. That was the procedure to have mobile charges beneath of this MOS system. Then let's think about this guy. If we wanted to just change its polarity, we wanted to now have mobile carrier when we have negative value, negative gate voltage. Then how can we achieve this goal? This goal is just achieved by if we decrease and if we decrease our gate voltage, then we will have a negative charge. Of course, this negative charge is provided from metal, so metal can always provide such kind of thing. It's okay, but point is this semiconducting part. If we first go down to certain voltage level, then our negative charges will be, our positive charges will be first provided from, once again, ionized impurity dopants. However, if we go further, far below that level, then due to duality, you can easily guess that what will happen to this guy. You will get mobile holes. That is the main conclusion of our discussion. So if we apply the negative voltage sufficiently, then eventually we will have negative, or we will have mobile holes. Then once we get mobile holes, and just like Nmos, these mobile holes collected just beneath of our Nmos system, yes, that can be used for current conduction. So amazingly enough, so we can find the dual device to our Nmos. So think about this guy. If we have Nmos, then if we have a high gate bias, then first we have dopant, so depletion of our system or our dopants, and it is just depletion of holes. After that, we have so-called inversion electrons, and we use only this inversion electron for our application. Then we can think about exactly dual device, like if we apply negative voltage, and once again we have a depletion charge. After that, now we will have inversion holes. Yes, then we will just use these holes for our electrical conduction. Okay. So do you have any question about my explanation? I guess that the first feeling is maybe to some of you, the first feeling would be life is not that simple. How can that can be true? How can you have this perfect duality between electrons and holes? Maybe not. Yes, I have to admit that this is really a special case for silicon. Unfortunately, we can find many different semiconducting materials. However, many semiconducting materials have only one preferred polarity. For example, many 3,5 compound semiconductors has only n-type dopants, effective n-type dopant, and it is very difficult to make p-type dopant. However, fortunately, in the case of silicon, we have almost well-balanced property between n-type dopant and p-type dopant. So that's the reason why we can achieve this kind of duality. So I think that is a really unusual one. So please don't treat it as granted. So there is not many semiconductors which can have this almost perfect duality. However, anyway, we are now using silicon. So in the case of silicon, we have a well-developed n-type dopant and p-type dopant. So we can make it in this way. For example, in this blue colored one, usually called as Nmos FET, we typically introduce p-type substrate. Yes, p-type substrate means that we prepare a lot of holes here. So think about this one. If this part is p-type, then we have a lot of holes and same number of negatively charged ions. And by depletion of our holes, yes, we just neglect this or remove these holes from the surface area, and we get negative charges. That was the point. Then now let's make it just a dual system. Now we have n-type reason. It means that we have a lot of electrons and we have the same number of positively charged ions. And if we apply negative gate bias to top gate, then what will happen? So now we have still depletion of our mobile carriers first. So we will get just positive ions. And after that, if we apply even more negative gate voltage to our gate, then eventually we will collect holes. So that is the realization of this duality, electron-hole duality. So are you all with me? So in principle, this kind of behavior can be realized to every semiconducting material in principle. However, unfortunately, there are not many semiconducting material which can provide us the really n-type dopant and p-type dopant simultaneously. So yes, and please try to name this device. So what will be the name of this dual device? If you have some choice or some freedom to name them, then maybe you will call it as P MOSFET. Why we call it as P MOSFET? Because actually this N, starting in alphabet N, starts from the negative 4 electrons. And now, since your device is now using holes which has the positive charge in it, so you are recommended to call it as P MOSFET. Okay, so then I want to ask you, how many in this world, how many P MOSFET exist in compared with our N MOSFET? So what will be the ratio? I have no idea. So if we, for example, if we consider really the system semiconductor chips like a logic or in your AP or whatever, then you have almost the same number of P MOSFET compared with N MOSFET. That is the case. And if I ask you another question, if we consider, for example, NAND flash device or DRAM, then how many P MOSFETs are there? Then my answer is almost nothing. So in memory device is almost perfectly made by N MOSFET, electron dominant devices, and logic chips are made of with the same number of N MOSFET and P MOSFET. Okay. So now, anyway, now think about then I just disclose the existence of this dual device called P MOSFET. Then let's think about its behavior. And when we have a P MOSFET here, let's make a comparison with our typical N MOSFET here. Let's say that this is N MOSFET and this is a P MOSFET. Then think about this one. Usually when you draw N MOSFET, where is your source? As I told you before, between source and drain, we have no predefined structural dependence. So when the lower voltage is applied, that is acting as the source. So if we just draw this diagram, like this is highly biased and this is lowly biased, then usually when we have N MOSFET, then yes, you can easily understand this terminal is working as the source of your transistor. Why? Structurally they are identical. However, since a relatively low voltage is applied, so this point is working as source in a exactly same way. Even in the case of a P MOSFET, there is no difference between source and drain. Then now, which one is working as a source? Now, due to the duality, we have to say that the terminal which is biased at higher bias, that should be regarded as source of our P MOSFET. So are you with me? And relatively highly biased one is regarded as drain of our N MOSFET. In the same way, using the duality, the bias with relatively lowly biased one is regarded as drain. Okay. Then of course there is only one single gate for both of our N MOSFET and P MOSFET. So unfortunately I just lost my control pad. I have a little idea where it goes. Oh, okay, good. Now, then this one is gate and this one is gate. Yes, they are gate of our transistors. So N MOSFET has only one single gate and also it has one single gate. Then let me just draw the output characteristics of this P MOSFET. Okay, still we have more than 10 minutes, so we can cover many of the interesting topics. So let me just think about this one. Up to now, I have drawn several times about the output characteristics of our Nmos transistor. Okay, so that was drain bias, so relative to source, and VGS. So let me just write down. If we have really low gate bias, what happened to this guy? Oh, since we have a low gate bias, that transistor becomes really highly conductive and no current can flow. That was for gate source voltage lower than threshold voltage. Okay, for example, if a threshold voltage is 0.5, then when you apply, for example, 0.1, 0.2 volt, then nothing, no current occurs. However, once we apply the gate voltage higher than threshold voltage, then now our transistor becomes more and more conductive. So now you will get certain kind of behavior like this. So yes, you have seen it already. So okay, so sorry about my ugly drawing. So my drawing is really ugly. However, the point is, okay, when you increase your gate voltage, then you have a higher and higher current. And yes, this saturation current level is also increasing. So that is the feature you can achieve. And here I made a really poor drawing, so don't make it as a reference. So sorry about that. But anyway, that was just a schematic diagram for our Nmos FET. You remember it. Then if I draw at the same time for our, oh, I made a really big mistakes here. Sorry about that. So I have to say, oh, really sorry about that. This y-axis should be ID, drain current. Then what will be now the operational graphs for our ID versus VDS. You know that now source is highly biased and drain is lowly biased. So if we have a look at this axis, then now our operational range should be located at here, not positive one. Means that your drain bias compared to your source bias in the case of a PMOS FET should be always negative. Why? It is actually the way we define source and drain of a PMOS FET. Always the highly biased terminal is regarded as a source and lowly biased one is regarded as a drain. So we have this range. And current, so since we have higher voltage and lower voltage, always current flows in this way. This one is highly and this one is lowly biased. So then from our convention for terminal current, do you remember it? So if we have a certain circuit element, if current is flowing into the device through that contact, that is regarded as positive. And if that escapes from this circuit element through that terminal, that is considered as negative. So certainly what we can say is the drain current, the current measured at the drain terminal of our PMOS FET should be also negative because current is now escaping from our transistor. So here this the third quarter of our graph is occupied by our PMOS FET curve, output characteristics of our PMOS FET. Then let me just consider if we apply, for example, this one. Yes, for example, if we just apply VGS equal to 0 volt, then there is no current. If we apply even lower current, then eventually we will have the threshold behavior. So after that we will have this kind of behavior once again. But please note that good, but please note that if we have this kind of behavior, then what is the gate source voltage? Oh, gate source voltage is VDD. No, it's not. When you have such a kind of a highly conductive behavior, the gate source voltage should be minus VDD. You know, this guy usually applied to the VDD, and our gate voltage at best can achieve the VDD. So the difference, this one is the reference and this gate voltage is the measured one, and at best it can be 0. And in usual case, if gate voltage just changed between 0 to VDD, then the voltage of gate reference to the source becomes always negative. The best case for our PMOSFET is this guy is biased to VDD and gate is biased to 0 volt. In this case, we have the largest voltage difference between them, and we will have, in that case, if gate is yes, this guy becomes 0 volt and this guy becomes VDD, then we will have a lot of holes collected in this channel region, and that channel region or holes in that channel region will conduct the current. That is the situation we will have. Sometimes it is really confusing, even to me or even to experienced researchers. Sometimes, oh, what is the sign? What is the value? So usual trick to remember it is always think it in the absolute way. You know that, for example, people try to make the Nmos and PMOSFET at the same time. Let's say your threshold voltage for Nmos is, for example, 0.4 volt. Then maybe if your technology is reasonable enough, then you can guess that your threshold voltage for your PMOSFET device would be minus 0.4 volt around. So engineers are really trying to match their absolute magnitude. So if we apply, for example, 1 volt to our gate, then yes, we will have positive 0.6 volt gate overdrive voltage. And if we apply minus 1 volt gate to source voltage, then it means that our gate overdrive voltage becomes minus 0.6 volt. So since everything in between this N-type Nmos and PMOSFET, they have a really duality. So usually people just think that the absolute value and assume the negative sign for PMOS quantities. Okay? So are you with me? So that's the reason why, although these kind of graphs will be the most how can I say correct one, if you have a look at the papers, the research papers, sometimes people draw in this way. Instead of this way, they just draw in this way for PMOSFET. What is it? They just take the absolute value of drain current. Or even sometimes we can find this kind of behavior. Overlapped graphs between MOSFET and PMOSFET. What is it? Then they just take absolute value of drain voltage too. So, but anyway, this one is most correct one, considering all of correct sign. And when you have this inverted, once inverted or twice inverted graphs, then please understand that it is just originated from negative sign related to the PMOSFET. Okay? So now we have just 2 minutes. So I will just think about how can we really achieve this or fabricate this device into our system. Oh, good. If we can make it at the same time MOSFET and at the same time PMOSFET, we will love it. Then how can we make it them at the same time on the same place? Means that nearby. The trick is amazingly simple and straightforward. The trick is like this. Yes, now we have silicon substrate, and in order to make an MOSFET, we need P-type substrate. At the same time, if we make PMOSFET, then we need N-type substrate. Oh, then what we do is just to divide the entire silicon wafer into 2 parts, and this is N-type and this is P-type. No, I'm just kidding. It's not. So I'm just kidding. The wafer thickness is about 600 micrometer. That is not very effective way to that. Instead of that, at the surface of this thick silicon, we just make a really shallow 2 parts. Yes, localized. And this one is designed for our N-MOSFET, and another one is designed for our P-MOSFET. So usually we introduce a very shallow wells are formulated, and this is for our MOSFET, and that will be our PMOSFET. We just repeat the same procedure twice, really twice. Oh, then means that you have to spend a lot more cost for same chip in order to make our MOSFET and PMOSFET simultaneously. However, in the last lecture, we will find that this is really worth to invest our cost. So you will find every beauty of this technology, which can support both of MOSFET and PMOSFET simultaneously. Okay, we are already 1 minute over, so I will just wrap up today's lecture.